Throughout this course, we're often going to be taking monotone transformations of functions to simplify the math while preserving the order. So, for example, if ice cream is better than pizza, which is better than broccoli, then when we rate these items, we can assign whatever numbers we want as long as we preserve the ordering. So we can say ice cream is a 7, pizza is a 5, broccoli is a 3, or we can say ice cream is 8, pizza is 2, and broccoli is 0. As long as the ranking is preserved, the numbers don't matter that much. By contrast, if these numbers were prices, so ice cream was $7 and pizza was $5 and broccoli was $3, then that would certainly not be the same as if ice cream cost 8 and pizza cost 2 and broccoli were free. A cardinal property is going to depend not just on the ranking, but also the specific value. So if we were to apply a monotonic transformation to the prices, that would not be the same thing. For example, quasi-concavity is an ordinal property, while concavity is a cardinal property. Likewise, homogeneity is a cardinal property. So let's say we have this function x1 times x2 to the k. This is going to be homogeneous to degree k. But if we were to apply any transformation other than just scaling up the power, it's going to lose this property. On the other hand, homotheticity is an ordinal property. So no matter what kind of transformation we apply to the function, we still retain this property that dx1 dx2, which is minus f1 over f2, or here, minus k times x1 to the k minus 1, x2 to the k times x1 to the k, x2 to the k minus 1, depends only on the ratio of x1 to x2. We can see that if we were to apply a transformation to f, the outer derivative would show up in both the numerator and the denominator and therefore cancel out. So dx2, dx1 would remain the exact same. We now turn our attention to integrals, which are like the inverse of derivatives. So if little f is the derivative of big F, then we can say that big F is the integral of little f. So if little f is fx equals x, then we can find big F by inverting the power rule. So we want to think about what function would have a derivative that would be exactly x, which here would be x squared over 2 plus c. When we compute integrals, we're always going to be left with an extra plus c at the end, since we can add any constant to this function, and when we take the derivative, it's going to disappear. And so therefore, when we're integrating, we can arbitrarily add a constant. While we had a number of rules for computing derivatives, computing integrals is not quite so straightforward. Sometimes, like we did here, we just need to guess a candidate function and check to see if it works. Other times, we might need to use a change of variable to reframe the problem. Or if we're trying to integrate the product of two functions, we need to apply a process called integration by parts. Here's some examples of some commonly seen integration rules. If we want to integrate x squared, that's going to be x to the third over 3 plus c. In general, if I integrate any power function, it's going to be x to the n plus 1 over n plus 1 plus c. Remember that the exponential function with its own derivative, and therefore the integral of e to the x is just e to the x plus c. And since we know that a to the x is just e to the x times log a, that's going to integrate to a to the x over log a plus c. If we're integrating 1 over x, Well, the power rule is not going to work here because here n is equal to minus 1, right? So n plus 1 is equal to 0, so we would have to have x to the 0 over 0. That doesn't work. The actual answer is that the integral of 1 over x is log of the absolute value of x plus c. If I integrate log of x, that's going to give me x log x minus x plus c. Since we can check this, if we differentiate this guy, applying the product rule to the first term, we have log x plus x times 1 over x minus 1. That's going to equal log x. One of the nice things about integration is that it's a linear operation. So if we're taking the integral of some polynomial, all we have to do here is integrate each of the terms separately. The sum of the integrals is the integral of the sum. Sometimes an integral can be simplified using substitution. If we look at this case, the integral of 2x over 1 plus x squared dx, we can see that the numerator is actually the derivative of the denominator. So let's let y is equal to 1 plus x squared. Then dy is equal to 2x dx. That's going to simplify this to just integrating 1 over y dy. And we know what that is. That's going to be log of the absolute value of y plus c. And then we can just substitute back in for y to get log of 1 plus x squared plus c. If we want to integrate the product of two functions, we can do this by looking at the product rule for differentiation. So let's say we have two functions u and v. Then the derivative of their product is u dv plus v du. And if we integrate both sides, we get that uv is equal to the integral of u dv plus the integral of v du. And we can rearrange that to get that the integral of u dv is equal to uv minus the integral of v du. For example, to integrate x times e to the x dx, we can let u be x and dv be e to the x dx. So v we get just by integrating dv, that's going to be e to the x, and du, u is x, so du is dx. Plugging these into the integration by parts formula, we get that this integral equals u times v minus the integral of v du. And we know that this part integrates to e to the x, therefore this whole thing becomes x minus 1 times e to the x. So far, we've been dealing with indefinite integrals, so we're computing the primitive or the antiderivative of a function. We also have definite integrals. So here, the objective is instead to look at the graph of some function and calculate what the area underneath that function is along a range from some endpoints a to b. So we can approximate the area by taking rectangular blocks of width delta x and dividing the graph into these rectangular blocks, and then taking the value at each sampled point. And if we sum up the area of these rectangular blocks, that gives us an estimate for the area under the curve. Mathematically, the area is approximately equal to the sum of fxi times delta x I over all of the i's. As we take the width of this interval to 0, we're going to get a finer and finer approximation of this area. And in the limit, we're going to get the definite integral from a to b of f of x dx. This is a definite integral. Of course, it is not at all a coincidence that these two concepts of the definite integral and the indefinite integral share the same name, because by the fundamental theorem of calculus, the definite integral from a to b can be computed by finding the primitive, in this case big F, and taking the value at b minus the value at a. So this tells me the relationship between the definite integral and the indefinite integral. This diagram illustrates how we would estimate a definite integral. We're going to take rectangular blocks of a fixed width under the graph and sum up their areas. As these blocks get narrower, we're going to get a closer and closer approximation. Integrals allow us to relate the concepts of stocks and flows. As if we integrate a flow function over some period of time, we get this total accumulated stock over that period. For example, suppose we have a flow function that tells us that the net population growth is itself growing by 2% per year. If we want to find the total increase in population over 50 years, we can integrate this function from t equals 0 to 50. To do that, we take the indefinite integral. This is an exponential function, so it's just going to be divided by this 0.02, evaluated from 0 to 50. So it's going to be 50,000 times e minus just 50,000. So 50,000 times e minus 1, or about 86,000. That means that if we have this flow function, the total stock we accumulate over 50 years is about 86,000. Another example we can look at is the cost of producing a certain quantity of input. So if the marginal cost is equal to 0.2 times Q, meaning that the marginal cost of producing an additional unit is increasing with each unit we produce, then integrating the marginal cost from 0 to 100 is going to give us 0.1 Q squared evaluated from 0 to 100, or 1,000. That means there's a total variable cost of 1,000 to produce the first 100 units. If we were to say at a fixed cost of 500, the total cost to produce 100 units would be 1,500. If we have a definite integral and we want to take the derivative of this whole thing with respect to x, that's just going to equal 0 because the definite integral is a constant and x doesn't show up anywhere in this expression. So the derivative of a definite integral over x with respect to x is equal to 0. If instead x is going to appear as one of the limits of integration, and I want to take the derivative of this thing with respect to x, I can use the fundamental theorem of calculus. That's going to be d of big Fx minus big Fa dx. This is a constant, so the derivative of the primitive, which just gives me back the function. If the upper limit of integration is a function of x, so I'm integrating from a to g of x, ft dt, and I want to find the derivative of this with respect to x, that requires applying the chain rule. So this is equal to the derivative of big F of g of x minus big F of a. I take the chain rule here. That's going to be f of g of x times g prime of x. If we have a function of two variables, and we're integrating with respect to x, then we can take the derivative with respect to y by just taking the derivative inside the integral. So this is equal to integrating the partial derivative fy from a to b. So far, we've been looking at static optimization problems, where we're optimizing the value of an objective function at a single point in time. We're now going to consider dynamic optimization problems, where we're going to maximize the value of some objective function over a period of time. So what we're going to maximize is some objective function over the time period t0 to t1. And this function is going to take as arguments not just our control variable ct as well as time itself, but also a state variable xt. Xt, the state variable, is going to evolve according to our choices. So dx dt is going to be some function g of xt, ct, t. So depending on how we choose the control variable, that's also going to influence how the state variable evolves. This means that choices we make in the current time are not just going to affect the immediate outcome, but the evolution of the state variable, and therefore influence outcomes further down the line as well. For example, if we have a limited supply of some resource, it might be wise to avoid overexploiting it, since the immediate benefit will be outweighed by the long-term effects of depleting the resource faster than it can replenish. Let lambda denote the value per unit of x, and note that this can vary over time as well. So we can think about lambda t as being the shadow price of our state variable. So continuing the example from before, we can expect that as we deplete a resource, the resource will rise in price, which means that the overall value of our remaining stock is not going to drop as fast as the quantity, and might in fact increase. Our total remaining value is given by lambda t times x of t, and applying the product rule, we have that this is equal to lambda t dx dt plus xt d lambda dt. And we know that dx dt is given by this function g. At time t, the decision maker is going to maximize the Hamiltonian, which is going to be the sum of the objective function, this tells me the current benefit, and d lambda times x dt, which reflects the change in the remaining value of the state variable. That's going to be lambda t times g plus xt times d lambda dt. These second two terms are going to reflect the future impacts of decisions that we make today. So this first term reflects how our choices today affect the state variable in the future, and the third term is going to tell me how the value of the state variable is going to change as a result of my choices. To maximize this expression, we have first order conditions with respect to the control variable c and the state variable x. From the first condition, we want to balance out the immediate gains from changing c against the value of future losses. And from the second condition, we're going to balance the gains from accumulating more of the state variable against the loss of value in x represented by the change in lambda. Intuitively, the first condition states that we shouldn't deplete the resource too quickly for the sake of immediate gains, while the second condition says that we shouldn't deplete it too slowly, since this will unnecessarily accumulate too much of the resource and reduce its value. Looking at a simple example, let's suppose that we have 1,000 bottles of wine and we want to consider how to best drink it over the course of 20 years. So the control variable Ct represents the consumption of wine at time t, and the utility function is log of Ct. So we have diminishing marginal utility. Our objective is to maximize our overall utility from time 0 to 20. The state variable in this case is the number of bottles we have remaining. So we're going to have boundary conditions x of 0 is 1,000. This tells me that I start with 1,000 bottles, and x of 20 equals 0, meaning that I aim to drink everything by the end of this period. The stock of wine is not going to replenish, so dx dt is just minus Ct. The stock is reduced by the number of bottles that I drink. That gives me the Hamiltonian. H is log of Ct plus lambda times negative Ct plus xt d lambda dt. Taking the derivatives of H with respect to C and with respect to X, we're going to see from the first condition that the rate of consumption is going to be inversely proportional to the value lambda. And from the second condition, we see that lambda doesn't change, so the value per bottle stays constant over time. This means that the best solution here is just to drink the wine at a constant pace throughout the entire time period. Now let's consider a more complicated utility function, c to the gamma over gamma. This is known as power utility or constant relative risk aversion utility, and we'll explain what that means later on. There's a special case when gamma is equal to 0 of log utility. And furthermore, let's assume that we discount future consumption at a rate of delta. So we're maximizing the discounted utility over time. So we're integrating u times the discount factor from 0 to 20. Looking at the Hamiltonian here, we see that only the first term has changed. So if we take the derivatives with respect to c and x, we get e to the minus delta t times ct to the gamma minus 1 minus lambda is equal to 0. The second one is unchanged, so d lambda dt is equal to 0. So once again, we have the condition that the value of the state variable remains constant at some k. If we plug that in here, we get that e to the minus delta t ct to the gamma minus 1 is equal to k, or that ct is equal to k to the 1 over gamma minus 1 e to the delta t over gamma minus 1. If we look at this function, since gamma is less than 1, that means that the consumption of wine is going to decrease over time because this exponent is negative. This reflects the fact that the future is discounted relative to the present. So we'd rather drink more of the wine now rather than saving it for later. Now let's do a brief overview of probability and statistics. A random variable is a variable whose value depends on the outcome of some random event. So for example, x could either be 1 or 0 depending on a coin flip. So 1 if heads, 0 if tails. X is a random variable here. Random variables can either be discrete, which means they take on a finite number of values, or continuous, meaning that they take on an entire range of possible values. The probability density function describes the probability that each possible outcome occurs. In the discrete case, the density function actually gives us the probability of each outcome. So if we sum over all of the possible outcomes, that adds up to 1. In a continuous case, there's an infinite number of potential outcomes, and so the probability of x taking on any specific value is 0. But if we integrate the density over the entire interval, that tells us the probability that x falls within that interval. If we integrate over the entire range of possible values, that's known as the support of x, that integrates to 1. Here we can see a few commonly used probability distributions. The binomial distribution is either 1 with probability p or 0 with probability 1 minus p. The uniform distribution has x taking on a value in the range a to b with equal probability. The exponential distribution has a density function that declines as x increases. Finally, the normal or Gaussian distribution gives us the familiar bell curve. The expected value of a random variable is the mean of all the values it can take. In the discrete case, we can find the expected value by summing all of the possible values multiplied by the probability. In the continuous case, we're going to integrate x times the density to get the expected value. We can also find the expected value of a function g of x by integrating g over the density of x. If we're integrating a linear function, gx is equal to ax plus b, so we're integrating ax plus b times f of x dx. That's going to be equal to a times the integral of x f of x dx plus b, or a times the expected value of x plus b. The cumulative distribution function, big F of x, is the primitive of the density function. So we can also define the expected value as integrating x over the distribution dfx. For the examples we showed earlier, the expected value of the binomial distribution is just the probability of getting 1. The expected value of the uniform distribution is going to be the midpoint b plus a over 2. The expected value of the exponential distribution is going to be inversely proportional to the rate variable lambda. And finally, the expected value of the standard normal distribution is just going to be 0. Alongside the mean, we often consider the variance of a random variable, labeled as sigma squared x, which measures how spread out the values are. The variance can be defined as the expected value of the squared deviation from the mean, though the easiest way to think about it is that the variance is the expected value of x squared minus the expected value of x squared. The standard deviation, or sigma, is just the square root of the variance. And this can sometimes be more useful than the variance because it's expressed in the same units as x itself, while the units of the variance are pretty difficult to interpret. Going back to our examples, the variance of the binomial distribution is p times 1 minus p, meaning that it's most variable when probability is equal to a half, so it's just a coin flip. For the uniform distribution, the variance depends on the length of the interval. It's going to be b minus a squared divided by 12. For the exponential distribution, the variance is 1 over lambda squared, meaning that the standard deviation is going to be 1 over lambda, just like the mean. Finally, for the standard normal distribution, sigma squared is just 1. From a standard normal distribution with mean 0 and variance 1, we can scale it to have any mean and variance that we want by applying a linear transformation. So if I multiply x by sigma and add the mean mu, that's going to multiply the variance by sigma squared and add mu to the mean. So that's going to give me a normal distribution with mean mu and variance sigma squared. Finally, we can consider the degree of co-movement between two random variables by computing their covariance, which is defined as the expected value of the products of their deviations from their means, or as the expected value of their products minus the product of their expected values. Note that the covariance is just going to measure the degree of linear relationship between x and y. So if two variables have no covariance, that doesn't necessarily mean that they're independent, because they could have some kind of nonlinear relationship. Therefore, we always need to be careful about distinguishing between random variables that are independent and those that are merely uncorrelated. If x and y are independent so that their joint density equals the product of their densities, then their covariance is going to be equal to 0, because we can take this double integral as the product of these two integrals. This is integrating x minus the expected value over the entire density, which is going to be 0. This is also going to be 0. The covariance also comes into play when we're calculating the variance of a sum x plus y, because unlike an expected value, which is a linear operator, variance is like a quadratic operator. I can think about this 2 covariance of x and y term as kind of being like the cross term. Obviously, this was quite a lot of math to go through, and while most of it should be familiar to you already, I wouldn't expect you to be able to perfectly recall all of it without some further review. It's best to use this chapter as a reference, as all these topics will come up in future lectures, and so you should be prepared to use the tools that we present here when they're needed.